picture this scenario. You're writing a nightly batch job.
Right. Just a relatively standard task for, like, a Tuesday afternoon.
Exactly. You need to deduplicate a list of customer records. So you write a standard nested loop. For every single record, the code just scans through all the other records to check if they're a match.
Super common.
Yeah, and you test it locally on your machine with about 1,000 rows. It finishes before you can even blink.
Oh, yeah. Feels totally instant.
So you push the code to staging, test it with 10,000 rows, and it takes, a fraction of a second. Completely harmless. The code goes live, months pass, and the business grows.
As we hope it does.
Right. But then suddenly, at 100,000 rows, this exact same job starts just chewing through the entire overnight batch window. And then boom, the milestone hits. 1 million customer records.
And that is when things get really bad.
Yeah, suddenly that harmless little loop becomes the exact thing tearing down your infrastructure. And you are awake at 200 a.m., staring at a Grafana dashboard with one eye open, just wondering why the CPU is pinned at 100%.
I've been there.
The hardware didn't suddenly get worse. The business logic didn't change. The code didn't rot. It's just that, well, the curve arrived.
The curve arrived. That is, like, the brutal reality of scaling software. And the most confusing part for an engineer in that moment is trying to figure out what broke.
Right, because we assume failures come from bugs.
Yeah.
Like a null pointer or a drop network packet.
Exactly, or a typo. But a fundamental algorithmic threshold was crossed. A loop over 10,000 items is a completely different physical event inside a computer than a loop over 10 million items, even if the syntax on your screen is totally identical.
Which is exactly our mission today. We're taking a deep dive into the hidden machinery of production systems. And to be clear right up front, this is not interview prep.
No, definitely not.
We're not doing whiteboard trivia or trying to hack a tricky puzzle to get a job. For you, the engineer writing code every single day in Python, Java, or Go algorithms are the actual physics of your system.
They really are. They dictate whether your application scales gracefully or turns into a massive incident.
So, if algorithms dictate whether our systems survive the night, it feels sort of strange that the entire industry has such a damaged relationship with them.
Oh, it's completely damaged. I mean, we constantly mislabel these failures in our postmortems. We complain about, quote-unquote, operational problems.
Right. The service got slow.
Exactly. We say the database query regressed or the ingestion pipeline stopped keeping up. We treat it like a plumbing issue, like a clogged pipe or a bad server.
But underneath, almost all of these are algorithmic problems.
Yes. We are hitting the mathematical limits of the data structures we chose months ago.
And I think part of the problem is that most developers learn algorithms in this purely academic setting. Proving theorems, calculating theoretical limits.
Right, in a classroom.
Yeah, and then the only other time they show up is during a job interview where someone with a stopwatch judges your worth based on whether you can reverse a linked list on a whiteboard.
It's terrible. It's like an academic hazing ritual.
Totally. You memorize the textbook, get past the gatekeeper, and then immediately forget it so you can get back to real engineering.
But that framing completely detaches algorithms from the physical reality of the computer. I mean, an algorithm is really just a description of how work grows as data grows.
So it's like a cost curve.
Exactly. Think of a bad algorithmic choice as a cost curve hidden inside your syntax. The code passes the linter, the unit tests are green, your peers approve the pull request.
Everything looks fine.
Everything looks totally fine. But the input size is this ticking clock, and it eventually pushes the execution into a completely different scale or regime. In production, algorithms turn back into reality.
Let's actually break down the math of that deduplication batch job from the intro. So you have 1,000 items. A nested loop means for every single item, you check 1,000 other items.
Right, 1,000 times 1,000.
Which is 1,000,000 pairwise comparisons. Now, 1,000,000 operations for a modern CPU is just a rounding error. It takes milliseconds.
You don't even notice it.
But scale that input to 10,000 items. The input only went up by a factor of 10, but the comparisons. 10,000 times 10,000. You are now at 100 million operations.
And then take it to 100,000 items.
You're at 10 billion comparisons.
10 billion. And the idea itself didn't get worse, right? It just crossed a threshold where the runtime became entirely dominated by the mathematical shape of the algorithm, instead of just the raw clock speed of the machine.
And this is where we have to translate the concept of big O notation out of the textbook.
Yes, big O.
You usually see it written as a capital O followed by some math.
Yeah.
But it isn't a stopwatch.
No, not at all.
It doesn't tell you how many milliseconds an operation takes. It's really simply a description of growth categories.
Right. And those categories describe the shape of the curve. So constant time, or big O of 1, stays totally flat no matter how much data you have.
Which is the dream.
It is the dream. And then you have linear time, which grows proportionately. Double the data, double the time. Logarithmic time grows incredibly slowly, flattening out almost immediately.
And then you have quadratic time.
Yes. Like our nested loop, which curves upward and violently explodes once the input gets large enough.
And production systems rarely fail at small numbers. They fail when you succeed.
That's the irony.
Right. A wildly successful product launch, a sudden spike in customer signups, a data set that just doubles in size over a year that pushes your input size into a new category of growth.
And the feature was perfectly correct in staging. But 6 months later, that old logic is suddenly the hottest bottleneck in your server fleet.
I'll be honest, though. My first instinct when the pager goes off for a slow batch job is not to, open my code editor and check my loops.
Let me guess. You open your AWS console.
Yeah, exactly.
Yeah.
I drag the slider to give the container 64 cores. I mean, in the cloud era, with on-demand computing, why can't I just buy my way out of a bad algorithm? Why do I even care about the mathematical curve if I can just throw massive hardware at the problem?
Well, cloud providers actually love developers who try to outrun quadratic algorithms
I bet they do.
because it drives up the compute bill exponentially. But here's the thing. Infrastructure can delay a bad curve, but it cannot repeal it.
It just kicks the can down the road.
Exactly. If your algorithm scales quadratically, throwing vastly more CPUs at the problem just lets you hit the exact same brick wall a few months later, but at a significantly higher financial cost.
Right, because if you have a quadratic algorithm and you pay to rent a server that is 4 times as fast, you haven't really solved the problem.
No, because the curve is squared. A machine 4 times faster only buys you the ability to handle twice as much data before it crashes again. Math outpaces your cloud budget.
Wow, math outpaces your cloud budget. But even knowing that math, it is so tempting to look at a modern, multi-gigahertz machine and think the raw speed just overrides the theory.
Oh, people argue this all the time.
Yeah, you'll hear engineers say, sure, Big O says this approach is theoretically slow, but on my actual machine, with my specific CPU architecture, it runs way faster than the quote-unquote efficient algorithm.
And that brings up this massive tension between theoretical asymptotic curves, which is really just a fancy mathematical way of saying how fast things go off a cliff when data gets big, and the physical hardware.
Right.
There are 2 massive mistakes engineers make when translating Big O to reality. The first mistake is dismissing the theory entirely because it hides constant factors.
Because Big O ignores the baseline speed of an operation.
Exactly. An engineer will point out that a theoretically worse quadratic algorithm is so simple that the physical hardware cache just loves it, which allows it to beat a complex, theoretically efficient algorithm. And for small data sets, they are absolutely right.
Because Big O isn't trying to predict the exact milliseconds on your laptop. It's just telling you which curve eventually wins the race over the long term.
Right. Now, the second mistake is treating Big O as the entire story.
Oh, yeah.
You can have 2 algorithms that are both technically Big O of n log n on paper, but in real wall clock time, one takes 3 minutes and the other takes 3 seconds.
Wait, really? The exact same theoretical complexity?
The exact same theory, but the physics are completely different. CPUs don't fetch single bytes of data. They fetch whole physical chunks of memory at once, which are called cache lines.
Okay.
So if your data is laid out sequentially in an array, the CPU already loaded the next item before you even asked for it. That is incredibly fast.
Because it's just grabbing the next block.
Exactly. But if you are using a linked list, chasing pointers across random spots in your RAM, to a CPU, that is like walking to another city to fetch a single book every single time you want to read a page.
That's a great way to picture it. So the theoretical slope is identical, but the physical work the computer has to do is vastly different. The mental model here is that Big O gives you the slope of the road. But constant factors like memory layout and cache locality tell you where on the road you start.
And you really have to understand both. The phrase constants matter more than asymptotics in practice gets thrown around a lot.
Yeah, I've heard that.
And it takes the reality of hardware and uses it as a dangerous excuse to ignore the math entirely. I mean, the fact that sequential memory access is physically faster than random access is true. The fact that garbage collection costs real CPU cycles is true. But optimizing those things on a bad algorithm is completely missing the bigger picture.
It's like being in a car, hurtling toward a concrete wall at 100 miles an hour. That is your quadratic algorithm.
Right.
And optimizing the constant factors, spending weeks making sure your memory access is perfectly sequential and your cache hits are maximized, is just like upgrading to a highly premium plush seat cushion right before the crash.
I love that. A beautifully optimized quadratic algorithm is still quadratic. A highly cache-friendly full database scan is still a full database scan. You have literally just improved the quality of the seat cushion.
So optimization has to happen in two distinct stages. First, you choose the right shape, the right algorithm, so the system can actually survive the data growth. And then you optimize the constants so the system becomes economically efficient to run.
Exactly. Teams get into massive trouble when they try to optimize the constants without first fixing the slope. You just cannot optimize your way out of a fundamentally broken mathematical curve.
Okay, so we've talked about these curves that smoothly and predictably explode as data scales. But let's look at operations that appear completely flat, the ones that look perfectly harmless, until the exact moment they lock up your system.
Oh, these are the fun ones.
Yeah. Let's talk about appending an item to a list. If you're coding in Python and call .append, or in Java and add to an array list, adding one item to the end feels completely free. It operates in constant time, big O of 1, but that operation is hiding a massive structural secret.
It really is. Under the hood, dynamic arrays are backed by a fixed block of physical memory. When you create a list, the computer reserves a specific amount of contiguous space. Almost every time you append an item, the computer just drops the value into the next empty slot. That is a true big O of 1 operation. It's instant.
But eventually that fixed block of memory fills up.
Right. And then what happens?
Well, think of it like moving into a new apartment. Adding a new chair to your living room takes 5 seconds. It's a big O of 1.
Yeah.
But eventually, your apartment is completely full. You can't fit another chair.
Not without breaking something.
Right. So to add one more piece of furniture, you have to go buy a brand new, bigger apartment, rent a moving truck, physically carry every single piece of furniture from the old place into the new place, organize it, and only then can you bring in your new chair.
Yep.
That single chair addition didn't take 5 seconds. It took all day. It became an O of N operation, directly proportional to the amount of stuff you already owned.
And that is the absolute core of amortized analysis. Amortized simply means averaged out over time.
Okay.
In a textbook, we still classify a dynamic array append as a big O of 1 amortized operation, because the massive, expensive resizing operation, the moving truck, doesn't happen every time.
This is rare.
Very rare. It happens infrequently enough that if you average the heavy cost out over millions of cheap instant inserts, the overall cost per operation stays completely flat. The system pays a massive tax once and then enjoys a very long tax-free holiday.
But if the mathematical average is totally flat and fast over time, a production engineer might wonder why they should care about the one rare spike.
Well, the problem is that your end users don't experience the mathematical average. They experience the spike. Relying only on the average completely hides latency problems and capacity cliffs that can take down an entire architecture.
Oh, wow.
Yeah. I mean, if you are running a real-time system, say a microservice handling payments or a healthcare API, a sudden latency spike because the runtime environment decided to halt the thread and copy a 10 million item array is a catastrophe.
Because the thread just locks up.
The thread locks up. The health check fails because the server stops responding. The load balancer assumes the server is dead and routes traffic to the remaining server.
Which immediately gets overwhelmed.
Exactly. They hit their own memory limits and trigger a cascading failure across your entire fleet.
And this pattern of mostly flat, suddenly expensive, is everywhere in backend engineering. Hash tables occasionally have to freeze and rehash all their keys to stay efficient. Distributed databases operate on this exact premise too.
Cassandra is a perfect example of amortized design.
How so?
Well, it accepts write operations incredibly fast by just dropping data into memory. It is practically instant. Eventually, it flushes that memory to disk as immutable files. But over time, you end up with thousands of tiny files. So Cassandra occasionally stops and runs a compaction process, merging all those thousands of files into one clean file.
Oh, I see.
During compaction, disk I/O spikes, latency increases, and the node works furiously. It pays a massive heavy tax so that all future read operations can be fast.
So if you only measure the worst single operation, the system looks terrible.
Yeah.
But if you only measure the average, you get completely blindsided by the spikes.
Exactly. Good engineering means knowing whether your specific service is sensitive to the average throughput over a 24-hour period or sensitive to the worst case, 99th percentile latency spike. Holding both the average behavior and the worst case behavior in your mind at the same time is the mark of a mature system designer.
That makes a lot of sense.
Yeah.
Now, if you are using standard libraries day to day, and you absolutely should be, you aren't writing a quicksort algorithm from scratch. You're just typing your variable, hitting period, and calling dot sort.
Right. Thank goodness.
Yeah. You aren't building complex B trees manually. You just type a SQL command and tell Postgres to create an index. It's so easy to assume that because the tools handle the implementation, the algorithmic trade-offs just don't apply to you.
We call that the abstraction illusion. And using abstractions is obviously the right move. Re-implementing a standard hash table poorly is not a badge of honor for a modern developer.
Definitely not.
But that dot on your screen hides a massive algorithmic contract you just signed your system up for. Your application still depends entirely on the mathematical limits of the abstraction you chose.
So data structures are essentially agreements. They are strict contracts negotiating which specific operations get to be cheap and what exact penalty you have to pay to get that discount.
That's a perfect way to look at it.
Like, an index in a database isn't a magical speed boost that you sprinkle on a slow query. It is a carefully chosen data structure that makes one highly specific family of operations cheap, explicitly at the expense of others. Let's actually break down some of the agreements we sign every day.
Yeah, let's do it.
Take a hash table like a dictionary in Python or a hash map in Java. What is the actual contract there?
Okay, so a hash table gives you an incredible agreement. Expected big O of one constant time to look up any key. You hand it a key, it runs a math function, and jumps straight to the exact memory location. It is blazingly fast, whether you have 10 items or 10 million.
But there's a penalty.
Right. The price you pay in that contract is memory overhead and the complete destruction of order. Because the hashing function scatters data randomly across RAM, customer A and customer B might be stored miles apart physically. You cannot ask a hash table for the next largest item or all items between 1 and 50. The structure simply doesn't know.
What about balanced trees, like the B trees that Postgres and mice will use underneath the hood for their primary indexes?
Balanced trees offer a completely different contract. They give you big O of logarithmic time for lookups and updates. Logarithmic time is slightly slower than a hash table, but in exchange for that tiny performance hit, the tree maintains strict, perfect ordering.
So you can do range queries.
Exactly. You can ask for a range of values.
Mm-hmm.
Give me every transaction that happened between Tuesday and Thursday, and the tree can traverse that exact slice of data instantly without scanning the whole table. That is why relational databases depend on them.
And then you have structures like a heap. A heap gives you logarithmic time to insert an item and logarithmic time to remove specifically the largest or smallest item in the collection.
And it does not care at all about the middle items. It only meticulously tracks the absolute extremes.
Which makes it the perfect agreement if you are building a priority task scheduler or a load balancer, where the only question the system constantly asks is, what is the absolute most urgent thing in the queue right now?
Exactly. When you view your infrastructure through the lens of these contracts, the entire architecture of modern software makes sense. A search engine ranking pipeline is really just sorting algorithms, heaps, and graph traversals working together.
Right.
A Redis cache is literally just a giant hash table wrapped in an eviction policy. An API rate limiter is just applying an algorithmic concept like a token bucket to count requests over time.
So the mindset shift for you listening is to stop asking abstract questions like, what is the best data structure? And start looking at the code to ask which specific operations are on my hot path and what complexity am I paying for each one.
Yes, look at the hot path.
Because when your systems behave well, these algorithms stay totally invisible. But when they behave badly under the brutal pressure of scale, engineers suddenly have to rediscover these contracts in the middle of a production outage.
And the goal is to see the machinery running underneath the code before the system breaks. High-leverage engineering is not about being the one person in the room who can derive a hyper-rare mathematical proof on a whiteboard.
Thankfully.
Yeah, thankfully. It is about having a rock-solid grasp of basic growth shapes and applying that knowledge early. The engineer who understands why a hash table wins in a cache, why a balanced tree wins in a database, and why a nested loop full table scan is about to ruin everyone's weekend, well, that engineer is invaluable.
Everything we've discussed so far has been mapping out the theoretical curves. We've talked about the shapes of growth and the difference between big O of 1, linear, and quadratic time. But this leaves a massive piece of the puzzle on the table.
It sure does.
What actually happens when these beautiful, perfectly clean theoretical curves collide with the messy physical reality of actual hardware?
And that is exactly where we are going in our next chapter. We are going to move away from theoretical growth curves and dive straight into physical memory layout.
Which is where things get really crazy.
Totally, because if you look at an array and a linked list in a classic computer science textbook, they look like roughly equivalent options. They both store sequences of data, they just have slightly different complexity tables.
Right.
But the moment you introduce actual CPU caches, pointer chasing, and physical silicon into the equation, that comparison changes entirely. What wins on paper might just crash your system in practice.
The physical reality of memory is where all the hidden ghosts of performance lie. We'll trace exactly how CPUs fetch data and why memory layout dictates your application's speed more than almost anything else. Until then, keep an eye on your hot paths, check your loops, and remember, the curve is always coming.